to welcome Dr. Vivienne Baldassare here. So she is coming to us from Yale. So she's been at Yale now for, well, she's just starting her second year at Yale. So she is a postdoc there. She has a prestigious Einstein Fellowship. Before that, she was a grad student in the University of Michigan. So she got her PhD there in 2017. So Vivienne studies EGN and supermassive black holes in dwarf galaxies. So that's what we're going to hear about today. And I guess a little bit more about using optical variability to find those EGN in low mass galaxies. So thank you.
Great. Thanks so much for having me. I'm really happy to be here and tell you about some of the work that I've been doing. So we know that all galaxies, roughly the mass of our Milky Way and more massive, contain a supermassive black hole at their center. But one of the big open questions is how these supermassive black holes form in the first place in the very early universe. And so one of the ways that we are trying to have a better understanding of how supermassive black holes form is actually by looking at the population of black holes in very small galaxies at the present day. Okay, so we're interested in how supermassive black holes form and grow. And it turns out that based on semi-analytic models, the fraction of black holes in low mass galaxies is expected to be sensitive to the dominant mechanism by which supermassive black hole seeds form at high redshift. So there are a couple of different ways that we think the seeds for today's supermassive black holes may form. One is stellar death models. So this involves the death of a population 3 star, which gives you a black hole seed that is maybe 100 or a couple hundred solar masses. Another way that these supermassive black hole seeds may form is through the direct collapse of very large gas clouds, which would give you a more massive black hole seed of maybe 10 to the 4 or 10 to the 5 solar masses. And what is shown here is the fraction of galaxies that contain a central black hole as a function of galaxy stellar mass. Above 10 to the 10 solar masses, no matter how these supermassive black hole seeds formed, you basically have every galaxy with a black hole. But below that kind of critical mass, you start to see a difference in the fraction of galaxies containing black holes depending on the dominant formation mechanism. So if they tend to form via the deaths of population 3 stars, then most galaxies at around 10 to the 9 solar masses will have a central black hole, whereas if they form via direct collapse, maybe 60% or some number that is not every galaxy in that mass range. So by trying to figure out the fraction of low mass galaxies that contain black holes, we may be able to say something about how the seeds form. Okay. Furthermore, the masses of black holes in low mass galaxies themselves are constraining. So this is some recent work by Gillian Bellaberry, and they looked at, they did simulations of about 50 dwarf galaxies with central black holes, and this is showing the fraction of the black hole mass that is accreted as opposed to mass from its formation. And what this is showing is that for the vast majority of black holes in their simulation, they grow by very little after they form. So they form and they maybe grow by 5% or so, but that's it. You know, you might get a handful that grow by 15 or 20%. So since these black holes in these low mass galaxies may not grow that much since their formation, just by measuring their masses, you may be able to say something about the initial masses of those black hole seeds in the very early universe. Unfortunately, detecting massive black holes in small galaxies is very observationally challenging. So for more massive black holes, we can look at the impact that they have on stars around them and do stellar dynamical mass estimates. But the sphere of influence for a black hole that is 10 to the 5 solar masses is just a few parsecs, and this is largely unresolvable even with HST resolution outside our local group of galaxies. So another way of trying to identify them is looking for signs of black hole activity. A very popular way of doing this is to use the BPT diagram, right, which uses the relative strengths of emission lines to characterize the dominant source of photoionization in a galaxy. So based on this relative strengths of lines like O3 and H beta, you can determine whether emission lines are from star formation or AGN activity. But what this is showing is that low metallicity can actually have the effect of pushing things out of the AGN region of the BPT diagram into the star-forming region. So this is especially a problem for low-mass galaxies, which tend to be lower metallicity, but even if you have an AGN, your narrow line ratios may not be what you think they should be. Another issue with trying to use optical spectroscopic diagnostics is that strong star formation can dilute the contribution of the AGN to narrow emission line ratios. And again, this is a problem for low mass galaxies, which tend to be more star forming. So there are lots of observational challenges for detecting massive black holes in low mass galaxies. We really like to find them because they can provide constraints on the masses of black hole seeds at high redshift. And so in general, our solution is to search for accretion signatures of black holes in low mass galaxies, and I'm going to talk to you about a bunch of those different ways that we do that today. So as recently as 2004, I think there were only 2 AGN known in bona fide dwarf galaxies, as in less massive than the Large Magellanic Cloud. But thanks to large-scale surveys, we've identified an increasing number of AGN in low mass and dwarf galaxies using optical spectroscopic techniques, X-ray techniques, infrared, and recently I've been doing a lot of work using optical photometric variability to identify AGNs in low mass galaxies. So these are the 3 that I've worked on that I'm going to touch on today. Okay. So as I mentioned, one way of identifying AGN is to use what is called the BPT diagram, which uses the relative strengths of these emission lines to characterize the galaxy as star forming, as having an AGN, or as some sort of composite where you have contributions to the narrow emission lines from both an AGN and from star formation. So this is some recent work by Amy Rines, where they looked at 25,000 nearby dwarf galaxies in the Sloan Digital Sky Survey and measured their emission line strengths. And what they found was 136 of these dwarf galaxies that had narrow emission line signatures indicating the presence of an AGN, so that these are galaxies falling in the composite region or the AGN region. So 136 out of 25,000, which was actually an order of magnitude increase in the number of dwarf galaxies known to contain AGN at the time. On top of that, they found 25 galaxies that had broad H-alpha emission, which can be the signature of dense gas orbiting around the central massive black hole. This plot is showing the positions on the BPT diagram of those 25 dwarf galaxies with broad H-alpha emission. And as you can see, some of them also have narrow line signatures of an AGN, but 15 of them have narrow line signatures in the star-forming region of the BPT diagram.
Do you know who B, P, and T were?
Baldwin, Phillips, Turlovich?
Very good. Mark Phillips has been doing supernovae for a long time. That's his like obscure question.
Yeah, so the issue for these galaxies in the star-forming region is that type 2 supernovae can also generate broad H-alpha emission. Since we're looking at very low mass black holes where the full half max of broad H-alpha is between 500 and a couple thousand kilometers per second, we do have to worry about potential contamination, I guess, from things like type 2 supernovae or other transient stellar phenomena like luminous blue variables that can generate broad H alpha with similar full width half maxes. So this is not really an issue for very massive central black holes where you have line widths of 10,000 kilometers per second, but for these little low mass black holes, this was a concern, especially for galaxies in the star-forming region of the VPT diagram, where we know there's recent star formation, and potentially could be that we happen to catch a type 2 supernova when the Sloan spectrum was taken. So this is showing the evolution of a type 2 supernova over the course of about a month, and you can see that you do get fairly broad H alpha emission there. However, the thing is with type 2 supernovae that these broad lines will fade on timescales of several years, whereas in general with an AGN you expect them to stick around, unless it's something like a changing look AGN, which are relatively rare. So what I did was multi-epoch spectroscopy of these dwarf galaxies with broad H alpha emission. So we looked at 19 broadline AGN candidates, and the goal was to determine whether the broad H alpha emission was from an AGN or a supernova. In the end, I got observations of 14 of the star-forming galaxies with broad H alpha emission, and then 3 composite and 2 AGN. And the follow-up spectroscopy was taken somewhere between 5 and 10 years after the Sloan spectrum was taken.
Sorry, what did you use? Was it fiber or slits or IMP?
Long slit.
So were you able to just sorry, words. Was it bright enough that you could actually isolate maybe the AGN versus the more extended emission from your host galaxies?
Sorry, in the follow-up spectroscopy?
Yeah.
So for this sample, we were trying to just figure out if broad H alpha emission was still there or not.
Okay, so not. Okay.
And so what we found was that for the galaxies that had star formation like narrow emission lines and broad H alpha emission in their Sloan spectra, the broad H alpha emission had faded in the follow-up observations, which were taken somewhere between 5 and 10 years after the Sloan spectrum. So this is just one example of a star-forming dwarf galaxy that has broad H alpha emission in its Sloan spectrum of a few thousand kilometers per second, full width half max. And then in the follow-up spectrum, the broad H alpha emission is totally faded, which suggests that this is from something like a type 2 supernova as opposed to an AGN. The next thing was that for objects that also had narrow line evidence for an AGN, so in the composite or AGN regions of the VPT diagram, the broad H alpha emission was still present in our follow-up observations. So these are 2 examples, one AGN and one composite galaxy, where you have broad H alpha emission in the Sloan spectrum, and then it's still present in the follow-up observation and consistent with the previous observations. And so for these galaxies, we can measure the black hole masses from the broad H alpha emission, and these are 2 dwarf galaxies with black holes of about 3 times 10 to the 5 solar masses. I'll just say a few words about using broad H alpha to estimate black hole masses. This is one of the only ways that we can measure black hole masses for these dwarf galaxies. If you assume that the gas in the broadline region is in virial equilibrium, you can get a black hole mass if you know the distance to this broadline gas and how fast it's moving. So the velocity of the broadline gas you just get from the full width half max of your broad H alpha emission, and then there have been a series of empirical correlations that link the distance to the broadline region, which has been measured by reverberation mapping, with the luminosity of broad H alpha. So you can get a black hole mass estimate just using the broad H alpha emission line, although there are large systematic uncertainties associated with this, about a factor of 2. But this is one of the only ways that we can measure black hole masses for these objects. So the take-home message of that project is that broad H alpha emission alone cannot be used as a way to select AGN in dwarf galaxies. For basically all of the galaxies that had broad H alpha emission in the star-forming region of the BPT diagram, we saw that that broad H alpha emission faded in follow-up observations, suggesting that it was not from an AGN, but instead from a type 2 supernova. However, the narrow line objects we feel confident are AGN. Their broad H alpha emission was still present in follow-up observations, and so those are fairly secure objects.
And so do you have like X-ray, radio observations?
Yeah, so I'll talk about the X-ray observations in a few slides of objects that have broad and narrow line AGN signatures. First, I just want to touch on one object that I've done a lot of work on, RGG 118, which was identified as having narrow lines in the composite region of the BPT diagram. It has a stellar mass roughly similar to that of the Large Magellanic Cloud. And then here I'm just showing a few different narrow line diagnostic diagrams. The blue point is the Sloan Digital Sky Survey spectroscopy, and then the red point is its follow-up spectroscopy with the Magellan Echelon spectrograph on the Clay telescope at Las Campanas. And so using all of these different narrow line diagnostics, there's evidence for an AGN in this galaxy. In the Sloan spectroscopy, we also saw hints of broad H alpha emission, but it was just below the flux detection threshold. With our follow-up Magellan observations, we clearly detected faint broad H alpha emission with a full half max of about 800 kilometers per second. And we can use this to get a black hole mass estimate, which gives us about 50,000 solar masses, which is one of the lowest mass black holes detected at the center of a galaxy. We got Chandra observations for this system, which revealed a hard nuclear X-ray point source with a 2 to 10 keV luminosity of about 5 times 10 to the 39 ergs per second, which gives us an Eddington fraction of about 1%, which is quite high. Okay, I got HST imaging of this system, which doesn't show up very well, but it's basically a very typical spiral galaxy. This is just showing the surface brightness profile. So the surface brightness as a function of the major axis. We did some modeling with Galfit and found that it was best described by an outer exponential disk, an inner point source for the AGN, and then a pseudo-bulge component with a very low Sirsic index. Might be able to see these a little better. This is just the near IR imaging of RGG 118, the best fit model, and then the residual. So we looked at where this system sits with respect to scaling relations between black hole mass and host galaxy properties like bulge luminosity and bulge mass. These gray points are more massive spiral galaxies. And then here I'm showing RGG 118 and a couple of other low mass galaxies with AGN. And so the black hole in RGG 118 seems to be undermassive with respect to the host galaxy bulge luminosity and bulge mass.
Sorry, what is the Milky Way? Is this the Milky Way also under massive or low?
I guess the Milky Way would be, well, yeah. I don't know what I would call the bulge mass of the Milky Way, but if you go total mass, I guess it'd be, maybe around here, right?
Yeah, around there. And the black hole is like 4 times the next.
Yeah.
Yeah, so it is undermassive.
So it is.
So it is a little
also
massive.
undermassive.
What's the total map?
Yes, the total, right.
The bulge is on
Yeah, so the question is, where is the Milky Way? Because we don't know what the mass of the bulge of the Milky Way is, right?
Yeah.
So it's gonna be like way to the, where you pointed was a total mass.
Right, yeah.
So it would be way to the left.
So
I'm
with
just
total
curious.
mass is somewhere around here, I guess.
Yeah, so if it was just a bulge.
Ten to the 10.
You think it's 10 to 10?
That's too big for 10 to 10.
So then No, I mean like on, no, I mean here.
If the bulge mass is 10 to the 10?
Yeah, and then if you put a black hole mass, oh,
Well, it's not good with
It's-
Cornell, but
It's
that's not-
consistent
it's
with,
consistent, okay.
with this work from Lasker, which was for other spiral galaxies.
Sure. Yeah, I was trying to, like,
Do you trust the blue line better?
no, I don't, I'm just like.
Well, they're different samples. So
Right.
The blue line is actually fitting more of the mass of them, so, from the, looked at more spiral galaxies, and so we're seeing this deviation. But if you're plotting the Milky Way on, with everything else, it is spiral massive, yeah.
Right. So the blue line is primarily defined using classical bulge-dominated systems with quiescent black holes, whereas this is looking at spiral. The pink line is looking at spiral galaxies with active black holes. We're also interested in seeing where these low mass systems sit with respect to the M sigma relation, so the relation between black hole mass and host galaxy stellar velocity dispersion. So these are the Cormandy-Ho classical bulges, and then these are the Cormandy-Ho pseudo bulges. And then I'm showing a few different fits that have been obtained to the M sigma relation. And interestingly, the low mass systems do seem to be somewhat consistent with the extrapolation of M sigma to the low mass end.
Sorry, I'm so sorry to interrupt.
Oh, that's
so
fine.
are you accounting for any observational biases on the lower left-hand corner of your figure?
Observational biases in terms of,
I was just curious. I mean, I know that obviously there's minimum resolution, so it looks like you aren't well above that. You see here, like above 20 kilometers a second or so.
so one big problem, I guess, is what do you define as the bulge for these
Yeah.
little galaxies? And basically, we're looking at a 3 arcsecond slit width, which at these distances is more or less probably about 2/3 of the size of the galaxy.
Yeah, so it's integrated like.
Yeah. So there definitely could be,
Maybe it could push to the left.
yeah.
Do these galaxies rotate? Sorry, I missed it earlier.
Huh?
Do these galaxies rotate?
I think so. At least RGG 118 is a very typical disky spiral galaxy. Some of the other ones are more elliptical in shape, but I think some of them probably do rotate.
If that's the sigma for the bulge.
It's the sigma
Your best
within,
estimate for the sigma.
sorry?
That's your best estimate for the sigma for the bulge, right?
Yeah, though what is defined as the bulge for these low mass systems is tricky. RGG 118 doesn't have a classical bulge per se, but more of a pseudo bulge, and so it gets tricky. Okay, so I'm going to switch gears a little bit and talk about some X-ray observations of these systems. So we got X-ray and UV observations of these broad line AGN in dwarf galaxies. This is showing the total sample of 11 systems. We had new observations for 8 of them. Most of them are in the AGN or composite regions of the VPT diagram, so they have broad and narrow line evidence for the presence of an AGN. And then we threw in this one kind of oddball suspected low metallicity AGN. So these are just the Sloan Digital Sky Survey images of a few of our targets. These are the HST UV observations. And then these are some of the 0.3 to 8 keV Chandra observations. What we found was that all of the dwarf galaxies with broad and narrow line AGN signatures are X-ray detected. Okay. So not only were they X-ray detected, but their X-ray luminosities were higher than would be expected from star formation. So this is showing the 0.5 to 8 keV luminosity as a function of star formation rate. And then the blue line is showing the X-ray emission that you expect from high mass X-ray binaries based on the star formation rate of the galaxy. And so we estimate the star formation rates based on the narrow H alpha emission. So these are all upper limits on the star formation rates anyway, since we know for these objects there's some contribution to the narrow line emission from the AGN. So they're all X-ray detected, and they're all significantly brighter than would be expected based on their star formation rates in the X-ray, except for this one object that was in the star forming region of the BPT diagram anyway. It was X-ray detected, but for this one we can't definitively say whether that X-ray emission is from an AGN or not. Since these all have broad H alpha emission lines, we can estimate Eddington fractions, and they range from about 0.1 to 50%. So these are accreting very, very rapidly. We also looked at the relation between the UV and the X-ray emission. So there's a quantity alpha OX, which is basically the ratio of the emission at 2,500 angstroms to the emission at 2 keV. And that's quantifying the relative power output that you get from the accretion disk, which is emitting in the UV, and the hot X-ray emitting corona. And there's been found a tight relationship between the alpha OX and the 2,500 angstrom luminosity for more massive AGN, which suggests some sort of scale invariance in the accretion properties of AGN. The population of AGN in these lower mass galaxies seems to be relatively UV bright with respect to the X-ray emission, and this has also been found in some recent work by Rich Plotkin looking at million solar mass black holes, that they seem to have a relatively bright UV emission compared to their X-ray emission. And so we're not sure yet what this is saying, but there may be some change in the accretion properties of these lower mass black holes as compared to more massive AGN. Okay, so for the last bit of my talk, I want to discuss some new work that I've done looking for AGNs in low mass galaxies using optical photometric variability. Okay, so AGN have been observed to vary at all wavelengths on a wide variety of timescales. This is just an example of very well-known AGN NGC 5548. Yeah, so you can just see that the flux is varying by quite a lot on timescales of months to years. The variability tends to be aperiodic, and the amplitude changes over time. And though the physics of this variability is not particularly well understood, it's typically attributed to instabilities in the AGN accretion disk. And optical variability has been a very prolific tool for identifying quasars and AGN. So what I wanted to do was look for optical variability in a large sample of nearby galaxies. So what I did was to do a difference imaging analysis of 28,000 galaxies in the NASA Sloan Atlas, which is a catalog of nearby galaxies within redshift of 0.15 that all have Sloan Digital Sky Survey spectroscopy and stellar mass estimates. And so we looked at galaxies that were in the NASA Sloan Atlas and in Stripe 82, Stripe 82 being this patch of sky that has been repeatedly imaged by the Sloan Digital Sky Survey for, I think the initial survey was 4 years, and then they had 4 more years of infrequent continuing observations. So we looked at these 28,000 galaxies, nearby galaxies in Stripe 82. This is just showing the positions of those galaxies on the sky, and then it's color-coded by how many epochs of observations we had. So we were using only photometric observations that were classified as photometric by Sloan, since we're interested in detecting very low-level optical variations. We put a lower limit of 10 epochs, which is the darker color, and then we have up to about 30 epochs in the brighter regions. Okay. So I'm going to go over some of the basic steps of our light curve construction. So we do a difference imaging analysis. Direct aperture photometry doesn't really work here since these galaxies are not dominated by the light output from the AGN. They're not point sources, so you really need to be able to subtract off emission from the host galaxy to have an idea of whether there's anything varying at the center. So the basic step, the first step of difference imaging is to construct a template image from your best frames. So your frames with the lowest background and your best seeing. So you have your best frames and you construct your template image. And then what you do is for each individual exposure, you convolve the template image with a best fitting kernel to match the seeing of whatever exposure you're looking at. So you're degrading the template to match your exposure, then subtracting the template from the individual exposure leaves you with a difference image, which should be dominated just by noise, except for any variations which will pop out against the background. We then construct a light curve using forced aperture photometry of the template and difference images. So we do this for all 28,000 galaxies. This is an example of a galaxy that is not varying. So you can see that it's really just dominated by noise. Nothing's really happening. And we measure the nuclear variability within a 2.5 arc-second aperture, which is just set to basically be a little bit worse than the worst case scenario seeing, to ensure that we're not missing any light from the center. Okay, we want to select galaxies that have nuclei that have AGN-like variability. And so to do this, it turns out that AGN variability is very well described by a damped random walk model. So we select galaxies as having AGN-like variability if they are variable with a certain significance, and if the significance that they're fit to a damped random walk model is better than random variability is greater than 2 sigma. And these are two examples of low mass galaxies that have AGN-like variability. So this is the nucleus magnitude in the central 2.5 arc seconds over time. So we've got about 8 years or so of data here. Let's see. I don't know why the bottom one plays first, but anyway, you can clearly see that there's something varying at the center. And here, the blue line is showing the best damped random walk model fit. That's the solid blue line, and then the shaded region is the model uncertainties. So these are both very well described by a damped random walk variability. These are showing just the images of those two galaxies and the 2.5 arc-second aperture in which we measure the nuclear light output. Often, a standard measure of variability is just the standard deviation about the median nucleus magnitude. So what this is showing is just the log of that standard deviation, right? So here you have a median magnitude of 19.6, and the standard deviation about that median for these points is 0.02 magnitudes. Whereas here you have a galaxy where the median magnitude is 19.3, and your one standard deviation scatter is 0.1. So here I'm just showing the standard deviation scatter as a function of the nucleus magnitude. So obviously we can detect fainter or more low-level variations in galaxies that have brighter nuclei. This is the entire sample of 28,000 galaxies. This solid line is just showing the median 1 sigma scatter as a function of the nucleus magnitude. These are all of our variable AGN candidates. So they all have scatter that is basically 1 sigma greater than you would expect for their nucleus magnitude. You can see that there's a bunch of other variable stuff up there. So some of that is the result of poor image subtraction. There might be a saturated star nearby that prevents you from doing a good job. Some of those are other variable sources. So like here we have what appears to be a supernova. And you can see that this is not very well described by a damped random walk model. This guy I think is so cool. I don't know what it is. It seems to be some kind of periodic variability, but it has a redshift that is about 0.04, so I don't know. But yeah, there's lots of cool stuff in this data set. Yeah, we're trying to think about whether any of the things that look like this may be tidal disruption events or not, so we'll see. Okay, so in the end, out of this 28,000 galaxies, we find 135 that have AGN-like nuclear variability. So this is just showing the breakdown in terms of stellar mass. The gray histogram is the full NASA Sloan Atlas sample of 28,000, and then the orange is our variable AGN. So they skew towards higher stellar masses. This is just showing their G minus R colors as a function of stellar mass. The underlying contours, again, is the whole sample, and then the orange data points are our variability selected AGN. So our sample skews towards higher stellar masses and bluer objects. So this is showing where they all sit on the BPT diagram. So they all have Sloan Digital Sky Survey spectroscopy, and then here the points are color-coded by the galaxy stellar mass, with the yellow points having stellar masses of about 10 to the 11, and then purple is about 10 to the 8. The little circles indicate the detection of broad H alpha emission. So what we found was that above 10 to the 10th solar masses, basically all of the variability selected AGN are in either the composite or AGN regions of the BPT diagram, and a large fraction of them, 80%, have broad H alpha emission. What I think is really interesting is that below 10 to the 10th solar masses, about half of the sample sits in the star-forming region of the BPT diagram. So that's these galaxies. So these are all systems that have AGN-like optical variability and sit in the star-forming region of the BPT diagram, so their narrow lines are dominated by recent star formation. So this suggests that these variability-selected AGN with star formation-dominated narrow emission lines could be AGN that are missed by other selection techniques. We also looked at the fraction of variable objects as a function of stellar mass. So that's what this is showing here, variable AGN fraction versus stellar mass. As you would expect, the fraction of variable AGN decreases with as you move to lower stellar masses. We wanted to make sure that this wasn't just an artifact of the fact that the lower mass galaxies are fainter. So this is showing the variable AGN fraction versus the nucleus G-band magnitude broken down by high and low stellar mass subsamples. So this is for galaxies greater than 10 to the 10 solar masses, and this is for galaxies below 10 to the 10 solar masses. So there does seem to be a genuine drop in the fraction of variability selected AGN with stellar mass, even when you account for this magnitude bias. There are a bunch of reasons why this could be observed. So there could be a genuine drop in the occupation fraction. Fewer galaxies down here contain black holes, so you observe fewer variable AGN. It could be that the black holes in this regime are undermassive, like I mentioned before, so you have some kind of change in the ratio of black hole mass to stellar mass as a function of stellar mass, which which would result in lower mass black holes and thus more difficult to detect via their variability. There could also be a decrease in the optical variability at low black hole masses and luminosities, or variability on different time scales. So we don't really know much about the variability properties of these low mass black holes. And so it could be that they may vary slightly differently than more massive ones. Okay, so I'll just spend a couple minutes walking through this plot. We wanted to understand what our detection limit was. So what population of black holes can we even hope to find given the SDSS stripe 82 sample? So what I'm showing here is the detectable AGN G-band luminosity versus redshift. So we basically looked at the population of low mass galaxies at each redshift and looked at the typical brightness within 2.5 arc seconds and determined what is the minimum variability that we could observe in a galaxy of this luminosity at this redshift. So this is just for the low mass galaxies. And this is assuming that about 5% of the total AGN luminosity is emitted in the G-band. And on the left, this is assuming that the AGN is varying at about 10% of its total luminosity. And here we're assuming that the AGN is varying at 50% of its total luminosity. So the purple lines are just showing the detectable AGN G-band luminosity as a function of redshift, given that if the AGN is varying at the 10% level and the 50% level. We then created a simulated sample of black holes based on different black hole to stellar mass relations and an Eddington ratio distribution. So here, the orange points are assuming a black hole to stellar mass relation that has been found for active galaxies. And then the blue squares are assuming the black hole mass to stellar mass relation that has been found for quiescent galaxies. So we saw earlier with the scaling relations that they differ for the active spiral galaxies and the quiescent bulge-dominated galaxies. And so we've just created a simulated sample of black holes based on these two different scaling relations between the black hole mass and stellar mass. And again here, the red points are based on the black hole mass to stellar mass relation for active galaxies, and then the blue are for the relation for quiescent galaxies. So we create 100 simulated black hole samples according to each of these scaling relations and levels of variability. So the histograms here are just showing the number of detections in the simulated sample. On the left, we're looking at the black hole population based on the relation for active galaxies, and then the relation for quiescent galaxies is on the right here. So we detect 35 galaxies with AGN-like variability below 10 to the 10 solar masses. And our simulated samples for the active galaxy black hole to stellar mass relation, for the 10% level, we expect somewhere between 10 and 20 detections, and if they're varying at the 50% level, somewhere between 40 and 75. And so our actual number of detections is in line with a population of black holes that is similar to what you would expect from the black hole mass to stellar mass relation for active galaxies. If they followed the black hole mass to stellar mass relation for quiescent galaxies, we would expect to detect many more, somewhere between 100 and a few hundred. Okay, so the take-home message of this plot is that if you look at the detectable AGN G-band luminosity versus redshift, we're only sensitive to a 10 to the 5 solar mass black hole accreting at Eddington out to about 0.05 redshift. So that's not particularly far, and most 10 to the 5 solar mass black holes are not accreting at their Eddington ratio. Most black holes of any mass are not accreting at their Eddington ratio. So we're definitely not detecting a complete population by any means. These lines are just showing the expected luminosity of a 10 to the 4 and 10 to the 6 solar mass black hole accreting at Eddington. So we're only sensitive to 10 to the 5 at Eddington out to about 0.05, but with LSST, which is going to have a single exposure depth that is a few magnitudes better than the SDSS, we should be able to identify a much larger population of these AGN and low mass galaxies that might be undetectable with other techniques. All right, so to summarize, I've talked about a lot of different ways of identifying AGNs and low mass galaxies. So with optical spectroscopy, narrow emission lines are a secure way of identifying AGN and dwarf galaxies, but they are incomplete. So we're likely missing a significant population where the narrow emission lines are either affected by low metallicity or the narrow emission line signature of the AGN is diluted by star formation. Broad emission lines in star-forming dwarf galaxies tend to fade on timescales of several years, indicating that broad H alpha emission by itself can't be used as a selection technique for AGNs and dwarf galaxies. We looked at the X-ray emission from broadline AGNs and dwarf galaxies, and those that also have narrow emission line evidence for an AGN have 100% detection fraction, and they're all accreting at very high Eddington fractions, ranging from about 0.1 to 50, so similar to much more massive quasars. And then with optical photometric variability, I identified 135 variability selected AGN in the NASA Sloan Atlas. And interestingly, at low stellar masses, about half of them are in the star-forming region of the BPT diagram, suggesting that using optical photometric variability may be a way of identifying AGN in these low mass systems that are missed by other selection techniques. So I will leave it at that. Thank you.
All right, does anyone have any questions?
So presumably you're already thinking about how this is going to work with LSST.
Sorry?
Presumably you're already thinking about how you might be able to use this for LSST.
Yes.
So what are your thoughts on that?
One of the things that I'm going to be working on next is doing some simulations with the LSST observation simulating software to try to figure out, based on the observing conditions and everything, what exactly LSST will be sensitive down to. 10 to the 5 solar mass black hole accreting at what Eddington ratio out to what distance. To be honest, more or less anything that LSST does will be an improvement, but obviously I'd like to be able to quantify that a little bit better. So that's something I'll be working on the next couple of months.
It doesn't matter to you what the observing cadence is for LSST. There's no real input that you, at this point, would say you have to do this.
One of the issues is that there's not much known about the variability properties of AGNs and dwarf galaxies. So one of the things that I'm hoping to do is a sensitive repeat imaging survey of dwarf galaxies with known AGN, so that we can have some better idea of what the timescales are that they vary on. The thing that matters for kind of the detection of them is you want repeat imaging in the same band, and I think that G band is probably the best bet for that. So that I think matters for this work. Cadence, I don't think we have a good idea yet, just because there's not a lot of information about the variability properties of known low mass AGN yet. But hopefully we can work on that before LSST. Yeah.
Someone else had a up here.
In your optical photometric study, do you know how many or what fraction of the variables that you found were similar to supernova-like curves?
I don't remember offhand, but there's probably a couple hundred at least. Yeah.
Because the fraction that you found in your earlier spectroscopic study of all of those star-forming ones fading away and possibly being supernovae, from a supernova person's standpoint, that's highly successful. We wish we could find supernovae that
Well,
efficiently.
for the broadline objects, you know, it was 15 out of 25,000 that basically happened to catch the broad H alpha emission from the supernova when the spectra was taken.
Okay, when you put it in terms of that, because previously you had like 15 objects in that part of the
Right,
the
yeah,
diagram.
so
All of
the
them
important
happen
thing to remember from that is that this was from a bigger sample of 25,000 galaxies. And the fact that you happen to catch 15 of them having some broad H alpha emission from a supernova is in line with expected supernova rates for the whole local universe as well. So it ended up being a low fraction of the total sample of 25,000 that were supernovae, but it was just that basically everything that had broad H alpha emission and star formation dominated narrow emission lines was a supernova.
But then also there were no star formation dominated spectra. They all turned out to be supernovae.
From the ones that had broad H alpha emission.
Right, the broad H alpha
Yeah.
emission.
Yeah.
Anything else?
Do you, or I guess, do people have a good handle on the distribution of Eddington values at low mass? Or is that still a little?
It's pretty uncertain. So some people would even argue that there is no dependence on the Eddington ratio distribution with black hole mass or with host galaxy stellar mass. We ended up using an estimate that was done for low mass galaxies below 10 to the 10 solar masses, but there's definitely some uncertainty there from